Hi and welcome back to my Physics Online video lecture series. Today's video we're going to be talking about 2D kinematics with constant acceleration. So this is part of a set or series of lectures that I'm doing on 2D motion and the description of 2D motion in kinematics. So today's video, the focus is what that would look like with constant acceleration, and maybe a little bit about what the 2D kinematics equations kind of could be seen to represent. Now that may be a sort of strange thing to say as an introduction to a video. What is it that I'm trying to get at here? Well, basically the way that we typically handle 2D and even 3D kinematics in an introductory physics course is that we typically sort of use the Cartesian approach to adding vectors together, but in most of the textbooks and in most lectures that's only kind of vaguely stated, or maybe not stated at all. You could, for what it's worth, do 2D kinematics or 3D kinematics and resolve everything vectors-wise using geometric tip-to-tail vector addition, but we typically tend to switch over to Cartesian coordinates to do that instead, or alternatively we switch over to whatever coordinate system the vectors are specified in. So what I mean by that is that probably the most common types of problems that you get in 2D kinematics, especially in algebra-based physics, would be like projectile motion. So this is the motion of an object which is projected. That means essentially tossed, thrown, shot, launched, flung, however you want to say, off into the air. And so, maybe you have a person standing on the ground and they throw a baseball forward and upward. So they like toss it to another person somewhere who's going to catch it. And once the baseball has left their hand, it basically undergoes freefall motion with maybe some air resistance, but we often neglect the air resistance. And so you have constant acceleration throughout this motion once the ball has been released, and the motion, even though it's taking place in 3 dimensions, can actually usually be solved in 2. Now I'm going to make a whole separate video just to focus on projectile motion. In fact, I may make more than one separate video for projectile motion. Today I'm actually kind of being a little bit more general. So let's start off with the lecture proper by sort of recalling what it is that we've done with constant acceleration. So when you have an object that undergoes constant acceleration, the sort of correct way of writing the equations of motion are that your x or y or z, your position vector, let's actually call it s here. S is given by 1/2 a t squared plus v initial t plus s initial. And I'm using s here to stand in for position. So s might represent x or y or z position. Well, this was for a 1D motion, meaning it's constrained to move only along, say, the x-axis, or only along the y-axis, or only along the z-axis. And we could similarly write that the velocity was given by the acceleration times time plus the initial velocity. And then 2 times the acceleration times the essentially distance traveled, or magnitude of displacement, is your velocity squared minus your initial velocity squared. And so this could be your final velocity, and this right here could represent S final minus S initial. So what's different when we go into 2D motion? Well, actually, all these equations that I just wrote are still valid. In 2D, and actually 3D for that matter as well, the same equations are valid. The difference is that every term now has an x component and a y component. So what does that really mean? Well, in some sense, we could say like but or caveat or something like that. In some sense, what that means is S might be now represented as x comma y. Or in other words, there's an x equation and there's a y equation. V would now be represented by Vx comma Vy. And of course these representations are in Cartesian, ergo why I'm using parenthesis here. Acceleration might be represented by Ax comma Ay. This right here also implies that the initial position Si is represented by x comma y initial, and then this one right here would be V is represented by, or V initial, excuse me, is represented by Vx initial comma Vy initial, etc. As an aside, if we wanted to go into 3 dimensions, we could use the same set of equations again, but we would have to add that third coordinate term. Okay, so coming back again to the 2-dimensional case, what this basically means is that instead of having these 3 equations like this, we actually end up getting a set of equations that may look like this. So we could say something like ergo, and then we could write one set of equations for y and one for x. So x would represent 1/2 ax t squared plus vx initial t plus x initial. And for the velocity along the x direction, I would have the acceleration x times time plus the initial velocity of x, and 2 times a sub x delta x would represent vx final squared minus vx initial squared. And along similar lines, I could write my equations for y to represent 1/2 ay t squared plus vy initial t plus y initial. And I could write my velocity for y to be something like ay times time plus v and y initial. And I could write my last equation, my time-free equation, as 2ay delta y minus, equals vy final squared minus vy initial squared. So instead of having 3 equations as I did in 1 dimension, I end up with 6 equations in 2 dimensions. And for that matter, if I go to 3 dimensions, I'd have the x's, the y's, and I could write like z equals 1/2 az t squared plus vz initial times time plus z initial, and vz is equal to AZT plus VZ initial, and 2 times AZ delta Z is VZ final squared minus VZ initial squared. So we just add like one more set of 3 equations and come up with 9 total in 3 dimensions. So what do these equations actually represent? So I've rewritten the equations here. We're going to call all of these collectively the x components, the x's components, the x parts, whatever you want to say, x equations. These collectively are the y equations. And yeah, this question is, what do they actually mean? And so to answer that, I would say, let me introduce an analogy which I call the shadow analogy. And the shadow analogy works basically like this. Imagine that I have an object which has a trajectory. Okay, so maybe the object in a series of snapshots carves out a path that looks like this. All right. Now, if you are able to just watch the object or the motion occur, you would basically see the object traverse this trajectory. But when you're modeling with these equations, you kind of get individual dots, and you end up getting individual dots for x and individual dots for y. So that kind of implies a sort of x and y axis, maybe like this. Whoops. My program's trying to screw me over by making very straight lines instead of just letting me draw a line. Okay. So we have a set of very nice x and y axes. And imagine that the x and y axis here represent maybe like the side of a building and the ground. And imagine that it is in like a dark room, maybe. So instead of the side of the building, maybe it's the floor and a wall. You're inside a very dark room, and this object is tossed. And you have 2 sets of lights. You have one set of lights on the far wall. So I'm going to draw the lights using kind of like yellows. You have one set of lights here on the far wall. So we'll call these lights. You have one set of lights on the ceiling. And you can turn on one set of lights at a time. So you can either turn on this wall's lights or you can turn on the ceiling's lights. Now, these lights are set up in such a way that both sets are relatively far away from the ball compared to this wall and the ground. So if I turn on the lights overhead, then as the ball moves, it should have a shadow that moves across the floor. Okay, so this light's far away, kind of like the sun. You get a shadow that moves across the floor for this ball. And so there's like a shadow here, 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 and here. And as the ball moves, the shadow also moves. Well, this shadow is moving according to the x equations. So moves, floor shadow moves according to x's. Okay, and then similarly, I end up with a wall shadow that is kind of going up, and then later it kind of starts coming back down again. Well, the wall shadow moves according to y's. And that's what these 2 equations are basically describing. If you don't like my shadow analogy, and some people don't, and that's okay, but if you don't like my shadow analogy, then I have a second way of describing this fairly simply, which is, again, consider this object to be in a room, and again, maybe you have a wall right here representing one side of the room. So this would be like a wall. And then over here would represent maybe the floor. And again, you have your object moving, and maybe the object is moving like this across the room. And maybe it's like an object that's been tossed or something like that, and it lands on top of a shelf, something like that. So what these things are representing, what these two equations are representing, are x's and y's. And so this distance right here, distance from this wall, could be represented by x as a function of time. So these would be the x's. And then the distance above the floor, we'll do that in maybe green, these distances right here, how high up is this object as it's kind of like completing its motion, these would represent the y equations. So x is basically telling you how far from the wall is it. Y is basically telling you how far from the floor is it. Thus, if I find after some amount of time that I've gone from, let's say, an x comma y initial of, let's say, like 1 meter comma 2 meters, and after 2 seconds later I'm at 6 meters comma 2.5 meters, it tells me that initially when I was at 1 comma 2 I was 1 meter away from the wall and 2 meters above the floor, and then finally I'm 6 meters away from that first wall and 2.5 meters above the floor. Alright, so let's go ahead now and work a quick example, at least for some definition of quick. So the example that I've written for this is kind of a long paragraph story form. You have a drone, like one of those little drones that you put a camera on and fly around to take pictures with. And you're out in maybe a canyon or something, so that you have a very tall cliff sort of behind you, and then a nice flat ground that the drone is hovering over. And initially the drone is starting off at this position of 3 meters from the cliff and 2 meters from the ground. So this whole statement right here would represent essentially your x initial comma y initial, and you could represent that, so this would be like s initial. This is 3 meters for x, 3 meters from the cliff, comma 2 meters. It's moving at a speed of 1 meter per second away from the cliff. This is still with the statement initially. So this means that v initial in this case, which would represent vx initial comma vy initial, is 1.0 comma 0. It's moving away from the cliff. It's not really moving up or down. And you can always put the unit outside of the parenthesis in Cartesian. And then we're also told that it's accelerating steadily. So it accelerates steadily by 2 meters per second upward and 1 meter per second away from the cliff. This is telling us that the acceleration ax comma ay, and this is worded, it's not really a trick question, it's fairly worded, it's just the order was flipped around because it tells you upwards first and then away from the cliff second. So away from the cliff properly goes with x, so the 0.1 meter per second squared goes with x. The 0.2 meters per second squared goes with the y, because this is upward. So upward means y, away from means x. And then we're asked, where will the drone be? Specifically, how far from the cliff and how high above the ground will the drone be 5 seconds later? So this is t. Alright, so that's kind of like the breakdown of the problem. Not a bad idea, by the way, to draw yourself a sketch when it's complicated like this. And you could draw it either graphically or whatever. You know, here's my drone initially. And I am told that initially it has a v in this direction, so v initial. I'm told that it has an acceleration that's more or less like this. So this is my acceleration. And for what it's worth, from the origin to here would be like my S initial. And so what I want to know is, given these conditions, where is this S final equals S at t equals 5.0 seconds. And I know that it's going to have taken some path to get here that's not a straight line because of this acceleration being not in the same direction as the initial velocity. So I'm trying to solve for that. So what I basically do is I can set up my equation or set up my system of equations, and I'm trying to solve for S final. So I only need the x and y equations. X and y equations. This is akin to saying S final is equal to essentially the 1/2 of a t squared plus v initial t plus s initial, which basically just becomes a system of two equations that are coupled in time. So I would have like x is 1/2 ax t squared plus vx initial times time plus x initial, and y is equal to 1/2 ay t squared plus v y initial plus y initial. And notice that that set of equations is the only one that I need to solve the problem I have. I don't really care how fast it's going or in which direction it's traveling at that time. I just care about where it is. So I basically just go solve these two piecewise. Alright, so to get the x part, I basically need the x initial of 3 meters. I need the v initial x of 1 meter per second. I need the ax of 0.1 meters per second squared, and I need the 5 seconds. And so I put all those things into my equation, and it basically looks like this. And so then I just solve. So in some sense, I have 3 terms that I just need to add to each other. I end up with x final is 9 or plus 9.25 meters. I'm not really paying attention to significant figures here. Okay. Then I do the same thing for y. Again, I basically have to go here and get the y components. So 2 meters for y initial, 0 meters per second for v initial y, and 0.2 meters per second squared for ay, and 5 seconds for time t. So I plug everything in here. This term right here should come out to 2.5 meters. This term is 0 meters, and then this term obviously is just 2.0 meters. And so I'm getting a final y, we can come up here, of 4.5 meters. And so my final position could be represented as 9.25, or if we care significant figures, maybe we'd say 9.3 meters, comma, 4.5 meters. And this tells me how far from the cliff and how high above the ground. So if I come back to this question over here, at this point we are 9.3 meters from cliff and 4.5 meters from ground. And we basically at this point solved a simple two-dimensional kinematics problem. In 3 dimensions, you just add one more set of these equations and one more set of these conditions to solve for z. So that one would basically be if we were in sort of like a I don't know, a cliff that makes an L shape like this somehow. And we wanted to know how far from this cliff face and from this cliff face and how far above the ground. But that's it. That's how we go about solving basic 2D or 3D kinematics equations with constant acceleration. So hopefully you learned something from this video, and thanks for watching.